Yeah, thanks for the intro, Jim, again. So I'm talking about Hamilton, an open source declarative micro framework. So it's not a fully fledged framework, it's a micro one that will help you write clean and robust transform code in Python. So essentially, as kind of Jim alluded to, essentially I'm going to be talking about how to write better code that will help you and your teams help yourselves. This is a short talk. Hamilton is open source. It is easy to get started. If you miss something, there should be documentation that will cover what's in this talk. So to start off, for those who don't know, I'm going to introduce what is Hamilton. In one sentence, I describe it as a declarative data flow paradigm. So it's a paradigm in that it's a shift in a way of thinking. So you kind of have to buy into the way of Hamilton prescribes. It's a data flow paradigm. So through it, you're going to be describing how data and compute movement kind of flows. And then it's declarative. So you're going to part of the premise of Hamilton is that you declare outputs as well as inputs very explicitly. And I'll show you that in just a second. So at a high level, if you're going to be using Hamilton, you're going to be writing some code that's going to describe a data flow that then you're going to use to kind of compute and get out some object. So you as a user will write Python code. You will then provide it to Hamilton so that your code will describe a data flow. This data flow Hamilton will turn into a DAG or a directed acyclic graph. And then you as a user will then tell Hamilton to compute something. So this could be pandas data frame, a machine learning model, or any Python object. You can kind of use Hamilton to create it. In terms of the actual code, like the things that you need to write, well, you need at least 2 files. So you're going to write your code and you're going to organize them to Python modules, and then you're going to write some driver code that will take those modules, tell Hamilton to build a DAG from it, and that's where you'll provide the right inputs and then say what should be executed for Hamilton actually to materialize a result for you. So what's this Hamilton paradigm? Well, here I have an example using pandas. So I have 2 lines of pandas code that create 2 columns, C and D. With Hamilton, you don't write kind of code in this style. Instead, you write things as functions. Now, these functions, you don't directly execute. That's why you need some driver code, which I haven't shown here, but I'll show in kind of the next slide. But essentially, the paradigm that you kind of think about is that if there is some output that you want, you essentially have to write a function that has that output variable, or where the function name is kind of the output that you're going to request. And then the function input arguments then declare what are the inputs required to actually compute a result. So to map this first line here, we're going to be writing, if you want to create a column C in pandas, that's the sum of A and B. You're instead in Hamilton going to write a function called C that takes in and declares A and B as input. Then the function body will have the actual computation. And then to create this column D, we then declare a function D, and its only input dependency is C, because that's the only thing that's required for it to be computed. Transform logic goes in the body of the function, and that's roughly how you write a data flow in Hamilton. Now, a full hello world, as I said, you kind of need this driver code, looks something like the following. So again, you write your functions and curate them to Python modules, and then you got to write some code to kind of stitch things together. So I call this kind of driver code, since it's kind of analogous to a Spark driver, for instance, since it helps drive kind of execution. You're going to be importing some modules from Hamilton. You're going to be importing your feature logic here. You're going to be instantiating what's called a driver object, which may or may not take in some configuration or initial data. You also then pass in the modules. From there, Hamilton will kind of scrape the modules, build a DAG, and then you're going to simply say tell Hamilton to execute something, and Hamilton will walk the DAG and only execute what's required to materialize the result that you want. So you might be thinking, okay, cool, that's a nice little paradigm, but why was it created? So let's kind of back up a little. So at Stitch Fix, there was a time series forecasting team called the Fed, and essentially their workflow looks something like the following. They got business actuals, created a featureized data frame, fit a bunch of models, which predicted the future, then they gave the business forecast. The biggest problem in their workflow in terms of delivering results was actually managing this kind of the code and kind of getting a featureized data frame, which is what Hamilton was designed to solve. Why was this an issue for them? So in time series forecasting, you run into this more sooner than other kind of modeling disciplines, but it's really easy to write a lot of features because features or columns, if you're thinking in a tabular sense, are just functions of other columns. So if you want to create more features, they're just derivatives of other features. So to create a holiday kind of feature, maybe you're just taking in year and week. I don't know, if you want to, create a new feature, maybe you're deriving something else. And so you can then come up with this kind of chain of dependencies of creating various features. And this is what was causing a bunch of issues for the team. So just to ground what I said in terms of some code, here is the characterization of the code they're kind of writing. So you have the Panda script. At the top of it somewhere, you load some actuals, say spend and signups. You then, start your featureization process. You add start appending columns. Maybe there's some configuration where, depending on what's passed in, you will have a different implementation of the feature. Then you'll just maybe you'll have some one-line incantations of features, or maybe you'll actually, have delegate to functions that will create these features for you. And then at the end of it, you're going to be, saving this for use for model training somewhere, or even just model training off of this directly. Now, this code looks pretty innocuous, pretty easy to manage. I want to say now, if you scale this code to, thousands of columns, and a growing team over the course of years, the code here and your process isn't going to look anything but clean and robust. Why is that? Well, if you think about unit testing and integration testing, unit testing here is pretty hard or non-existent if you write a lot of things in script form, especially if you do these one-liners. If you want to, do an integration test, or say you add a new feature, you even though you don't need to compute all the features to test that one thing or that chain of dependencies, you are stuck running everything to test one thing. Then there's code readability and documentation. Give this to a new hire. They're gonna scratch their head and have to literally read every single line of code and then try to draw this a mind map of how everything connects, because there isn't really a natural place to put documentation or even segment the code in a nice way if you're unfamiliar with how to do so, right? And then what happens over time is you're going to have updating code. Maybe there's some upstream dependencies that change. You then have to know the downstream impacts of in which case, if you write code in this manner, tracing lineage is difficult. Would you know that if you were to change acquisition costs, that actually this could impact this spend B feature? It's not obvious unless you read and understood the code, right? And then if you can now, you have a growing team, things are happening, how do you actually reuse things? Well, if you write the things in this form, everyone says, oh, I'll refactor later, but that generally never happens. It's always easy just to cut and paste, and then you have duplication everywhere, and then that becomes, adds to your maintenance burden. So that was the motivating things for building Hamilton. So, so Hamilton at Stitch Fix, well, it's been running for over 2.5 years, probably almost closer to 3 right now. And the Fed team who we designed it for, manages over 4,000 feature transform definitions with it, where all feature definitions are unit testable, documentation friendly, and centrally curated, stored, and versioned in Git. So this is a nice versioning story that they have. Otherwise, the data science teams who use it at Stitch Fix love it, and we've seen the best adoption from active time series forecasting teams, because they're the most willing to pay the migration costs. So Hamilton isn't a drop-in replacement. You have to re-engineer or rewrite some code to make use of it. And along the way, we actually found that it's actually by writing Hamilton code, it actually was a productivity improvement for the team, since they used to have the Fed team used to have a monthly feature update and model fitting task that used to take on the order of a day. Now it takes less than 2 hours, so it's 4x faster, and the only change is by using the Hamilton paradigm to write their code, which I think is pretty neat. So okay, so to the theme of this conference, feature engineering. So how to use Hamilton for feature engineering more concretely? Well, we have this rough schematic here for modeling things. So you have a featureization step where you're loading data, transforming the features, you're then fitting a model, and then you're using that model in production to predict stuff, and then passing in features there as well. And I want to say with Hamilton, you can actually model your entire machine learning workflow end to end if you wanted to. But just for this talk, going to focus on featureization. I will also kind of focus things on pandas, just because I think that is, the most common kind of thing that people know and understand. But Hamilton isn't beholden to pandas. So if you want to do NumPy stuff or your own custom kind of Python objects, Hamilton can support you there. We're just going to, for the rest of this talk, I'm just going to assume you know pandas, and the examples are therefore going to be oriented that way. You can Hamilton is a micro framework. It doesn't replace an orchestration system. So to use it for featurization, you would embed it, say, within Airflow, Metaflow, whatever your orchestration system of choice is. You could run it in a Jupyter notebook. This could be used in front of Feast. So create the features to then push to Feast. And then you can also use Hamilton in an online setting, since it's a very small Python dependency footprint. It can run in an async IO environment, so it's very easy for you to potentially even reuse your feature definitions from batch to an online or streaming settings, as long as everything runs Python. So onto featurization. So if you are going to use Hamilton featurization, you need to write at least 2 files. Say, you need to write something that will, potentially load data and, have your feature transform code, say features.py. And then you need to write some sort of run.py file or driver file, as I've referred to earlier, that will, take these feature definitions, create a DAG from it. And then that's where you kind of specify, what you want computed, where you can, so you can specify the superset of features, and Hamilton will only walk kind of the DAG for the things that you've requested. So in terms of the actual code, so thinking now, so one, you need to write functions to load data. This is where you kind of normalize naming of features or inputs. You need to create a common index to ensure that things join on. Then you're going to be writing kind of your feature functions, and optionally you can model your actual model fitting and prediction stuff if you want to as well. And then you're going to be writing these kind of driver files to kind of actually orchestrate and materialize data. And as I said before, with Hamilton, you can kind of build up this kind of bank of features, which can be the superset of what you need. And in a driver, you only request the things that you want, and Hamilton will only walk the DAG for what's needed. So pictorially, with Hamilton, for every kind of input, you'd be writing some sort of generally some function to load it. Then from those functions, you'll then be kind of writing your actual feature transforms, and then you'll be writing some driver files that will actually specify what you want computed to kind of compute a, say, data frame for model training that you want. In terms of general problems with feature engineering, just to kind of touch on this, that will bring things back to the robust and clean side of this talk. So from the human and team side, as it was with the Fed, kind of the examples, it's really easy to write highly coupled code that is really difficult to take out of different contexts and reuse, and so that adds to your maintenance burden. If you want to reuse and understand other people's work, most people actually rely on materialized data at rest to kind of do that. But with Hamilton, I think we have a better way with code to potentially do that, since we kind of facilitate and make a code reuse easier. And then if you do have things in production, generally things break. And that it can detract from your time. Hamilton has a few things there. Otherwise, from the machine front, just to touch on it, if data is too big to fit in memory, you need to figure out how to scale your computation. Similarly, if you want more throughput, you got to figure out how to parallelize it. And so I want to say Hamilton was designed for the human and team side, but also has a few hooks for scaling things on the data and compute side. But for this talk, I'm just going to focus on kind of the human aspects of things. Okay, and so how does Hamilton actually make feature engineering clean and robust? So as I mentioned, with highly coupled, it's easy to write highly coupled code, especially if you're writing pandas in a kind of script form. But with Hamilton, you're kind of forced to decouple your functions, your transform functions from the context, from the driver of where they're actually used. So it's very hard to actually write coupled code with Hamilton. And then because you're forced to curate your functions into modules, it's much easier to kind of reuse and understand people's work, since you're forced to kind of curate from day one. You're not going to be appending things to a script willy-nilly. You're going to be placing them into a specific module. Every function is unit testable. So if you want a good testing story, it's very easy to be test driven with Hamilton. Documentation is natural, since you can reuse the function doc. And then with Hamilton, just because of the way that things are stitched together, you are forced to align on the naming of them. So there is no foo bar variables or things that don't make sense, because you're kind of forced to make sure that people understand and can use the outputs. And so therefore that's also reflected in the functions and the code you write. And then in terms of, helping with production issues with Hamilton, the idea is, if there's an output, say a particular feature, there's only one place where that code is defined. Then it's very easy to go to the code definition and understand, what are its input dependencies. And so then it's very methodical to methodically debug issues. Because you're forced to curate things into a code base, it's very easy also to version features with Git and packaging. So if you need to roll back, there's a very kind of straightforward way to kind of do that. And then Hamilton also has the ability to do some runtime data quality checks without you having to install, something very, heavyweight such as Great Expectations. So just to give you a bit of a flavor and example of like what a Hamilton function is. So here's a function you likely haven't seen before. I want to say, take a few seconds to try to read it. It should be fairly understandable to you, and that's part of that was part of the design philosophy with Hamilton, since you read code more often than you write it. So how can we make it much easier to hand off code and inherit to people who have no context, right? So specifically, just to hammer home the points here, so with this function, it's very easy to unit test. We haven't leaked how to get data in, so it's very easy then to come up with a unit test that injects the data that you want to test the logic. Documentation is pretty easy and natural, since as you might have guessed, there's this app tag annotation, so you can add in different metadata if you wanted to help understand who owns things or impacts. We can actually visualize things, since we by definition have a data flow that we can then Hamilton outputs a graph as visualization for you pretty easily, and then you have the function doc string as well as the names of the function and input, so that make documentation very natural with Hamilton. Again, modularity and reuse, you're forced to curate these functions into modules, which are decoupled from drivers, so you can have a lot of different contexts that reuse the same modules. And so your maintenance story is much easier there, since you only have to, if logic changes, you only have to change it in one place. And then what happened at Stitch Fix was the team actually built up a central feature definition store. So basically they built up a little code base where they aligned on naming, curated things into modules, and by using Git had a very nice versioning and lightweight story of just of how to maintain features and go back in time and understand why things changed. And then you might have guessed, and I didn't tell you, but this @check output annotation is just a lightweight runtime data quality check that it was specifying that, hey, the expectation of this output is a float, and it should be between the ranges of -5 and 5, and there shouldn't be any NaND values. And so that's kind of a rough sketch of the Hamilton functions and why I think they help you write clean and robust feature engineering code. In terms of code-based implications, like I think we generally forget about this as we're writing code, how we actually structure our code base. Well, with Hamilton, just to hammer home these points again, it's like functions are always in modules, and then you write JavaScripts that actually contain context for how things are executed. They're very decoupled from those functions, so you end up curating modules. And then creating very separate driver scripts so you get code reuse from day one, so you can have a single kind of definition and then different contexts that can reuse it. And then generally from a maintenance perspective, if things change or inputs change, you only have to change this one driver script. You don't have to change all your feature logic, or and so maintenance and updates are easier there. And then your code base ends up being pretty well structured, so you can give Hamilton to a junior data scientist and they will write maintainable code. So to kind of summarize this talk, so Hamilton is a declarative paradigm that essentially helps you to describe your feature transforms and is embeddable anywhere that Python runs. It grew out of a need to tame feature code base at Stitch Fix, and go ahead and try it. I'm sure it'll make yours better too. In short, Hamilton essentially allows you to write clean and robust feature transforms by essentially getting you to write to practice software engineering best practices without you having to know it. And essentially, it's my goal, and I think a firm belief that anyone who's doing feature engineering in Python should know about Hamilton, because I think it's a useful tool to have in your back pocket if you're going to be writing code that you want to live for a while. So again, Hamilton's open source. Do go ahead and try it. Star us on GitHub. We are trying to curate roadmaps. So if you find issues or want features, you do create issues on GitHub. We also have curating a Slack channel, so if you want to come or if you have ideas and need help, do join us. Otherwise, that's the end of my talk. Thank you, and happy to take questions.
Thanks, Stefan, very much. It's very fascinating work that you're doing at the moment on Hamilton, and I think it complements many of the feature engineering tools that we use, like Pandas, very well. And we have one question that I think we have time to take. It's about, if you click on the Q&A, you'll see it in more detail. It's quite a long one. Is there anything that prevents the developer from forgetting about existing columns, of which there are many, and recomputing a column that is used as an intermediate for the desired feature? For example, an enforced single computations for a feature function. Maybe this issue ends up being picked up in post-monitoring.
If you define the same function with the same function and the same module, like Hamilton won't be able to pick that up. But if you define them in different modules and try to construct a DAG with them, Hamilton will tell you, hey, look, you got two definitions, something's broken, and it won't allow you to kind of proceed. So we've tried to ensure that we have, some static analysis checks when you build the DAG to kind of help with some of those issues. But yeah, the only one we can't catch due to Python actual limitations is if you define the same function twice in the same module. But generally, that's your IDE can generally tell you that, and so hopefully that's caught that way. Otherwise, I think to Jim's point, like Hamilton kind of complements a lot of the tools here. You can run it in front of things if you wanted to, hook it into data quality on the output of things. It's kind of, Hamilton gives you a lot of flexibility there to do so as well.